Thanks again for staying here. We are happy to have Miranda, who was a PhD student at Columbia. She's going to be a postdoc at MIT, and she's done a lot of foundation work on trying to understand watermarking in modern AI and connections to pseudorandom code, and she's going to talk about it.
Thanks. So I'm going to be talking about a problem in, I guess, trustworthy AI that has been especially friendly to theory. And so I have a couple of goals in this talk. One is just to illustrate a problem where I think theory has had some success, and maybe we can use this to tell us some things to look for in other problems in trustworthy AI where we can really contribute. I'm also hoping to tell you about this particular problem and show you some open questions that maybe you can work on if you're interested. And I also want to say a lot of the work I'll be talking about is joint with Sam Gunn, who is also here at STOC, so you can talk to either of us about this work. Okay, so the problem I'll be focusing on today is distinguishing between content that was generated by a human versus generated by an AI. And when I give this talk, I regenerate this image, and it gets better and better every time. So maybe now you can still tell that this was AI generated, but soon you can imagine that you completely won't be able to tell whether this is a real picture of me giving this talk or something that I just used ChatGPT to generate. And so if you want to tell if some content was AI generated, there is one maybe obvious approach, which is just to train a classifier to do this for you. And so there are a couple of classifiers that are available online that you can actually query with some content, and they'll tell you whether they think it was AI generated. But there are some issues with this approach. One is that often you can actually evade these detectors by asking the model very nicely to make sure to evade AI detection tools. And another problem is that, for example, one of these detectors is very confident that the US Constitution was AI generated. And so this is a little bit funny, but this unreliability has had some real world consequences. So some students have been falsely accused of cheating using AI because of these false positives. And it turns out that these false positives are more prevalent among non-native English writers. And so as a result of these issues, a lot of organizations have moved away from using these classifier-based detectors. And I think there's a real fundamental issue with using classifiers, which is that they're kind of forced to rely on markers of AI-generated content that just happen to exist today. And as we train these models to generate content that is more and more realistic, we're really removing these markers that detectors rely on. And the idea behind watermarking, which is what I'll focus on today, is instead of having to rely on these existing markers, maybe we can change the model to embed the markers ourselves in a more controlled way. And I'll be focusing mostly on watermarks for language models, where there has been a lot of work from the theory and cryptography communities lately. And all of these watermarks use the idea of embedding some kind of hidden pattern in the text that you'll look for at detection time. And basically, all of these works sort of choose each word in the text according to a secret rule. And if you know the secret rule, then you can detect the watermark just by looking for this pattern. And so there has been now a quickly growing line of work that sort of started with a watermarking scheme by Scott Aronson and one by Kirchenbauer et al. In 2022 and 2023. And what really separates this watermarking approach from the classifiers that I showed before is that now that we're embedding the markers ourselves, we can actually achieve provable guarantees from the watermark. So we can really control and prove bounds on the false positive rate. Okay, and to tell you a little bit of history about what happened in practice, these first works that I mentioned by Aronson and Kirchenbauer et al. Really distilled the problem nicely and made it easy to work on without needing to know much about how models actually work. They sort of distilled it simply enough that there was a New York Times article that was able to explain kind of the basics behind one watermarking scheme. Also, Scott's watermarking scheme was developed for OpenAI, and they didn't end up deploying it. Scott gave a talk that kind of explained this at Simon's. There was also a Wall Street Journal article about it. So if you're interested in what happened in practice, I'd recommend looking at these sources. And Scott, yeah, there was a comment on the YouTube video of Scott Simon's talk, which was like, wow, this is so interesting. I can't believe that OpenAI let him say this. So you might want to check this out. But on the positive side, a lot of watermarks are actually deployed today. So be careful if you're trying to pass off AI-generated content as your own. Google right now watermarks most text that's output by Gemini, as well as images, video, and audio. Meta also has a watermark, and Amazon as well. So these watermarks are not just theoretical objects. They're really used in practice right now. Okay, so now I'll move into showing you what a watermark is and some ideas behind building them. At a very high level, a watermark modifies an LLM. And what an LLM is you can think of it as a randomized algorithm that takes some prompt, say write me an essay, and samples something from a very large distribution of essays. So importantly, these algorithms are really highly randomized. You can ask for an essay over and over again, and every single time you'll get a different essay. And what a watermark does is it changes this model to sample essays from a slightly different distribution. So the watermark simply changes the distribution of essays that the model samples from. And so the first goal that we have of watermarks is to actually detect them in the content that the watermark model generates. And so detectability says that on one hand, if the content is actually generated by the watermarked model, then some detect algorithm should output true with probability close to 1. On the other hand, if you have an essay generated by a human, then the detection algorithm should output true with probability very close to 0. And the other guarantee we want from our watermarking scheme is we want it to preserve the quality of the model, right? In practice, this model is something that we worked very hard to train, and so we don't want to make the essays lower quality by introducing a watermark. And so ideally, the distribution of watermarked essays should be very close to the distribution of unwatermarked essays. And by the way, please feel free to ask questions at any point. Yeah. Good question. For now, you can think of this as, say, close in statistical distance, but we'll revisit it shortly. Okay. And so many of the watermarks that I already cited kind of exhibited a trade-off between these two properties that we want. The better detectability you have, the worse quality you have. So there seemed to be some kind of barrier that you couldn't cross. If you wanted better detectability, you would have to give up on quality. Okay. And so the best way to see why this apparent barrier was occurring is to walk through a simple watermarking scheme. And so I'll do that first by telling you just a little bit about how LLMs work. So kind of all you need to know about LLMs to work on watermarks is that they work in the following way. They take as input some prompt, and then they sample text token by token, where to compute the next token, we'll input the prompt and the text output so far to a neural network that computes a probability distribution over the next token. So this p sub t plus 1 is a probability distribution over the next token. To get the next token, we simply sample it from this distribution. We append it to the text generated so far, and now we continue sampling tokens in this manner until we reach some special done token that indicates that it's the end of the response, at which point we just output the entire response. And basically all watermarks just alter the sampling step. So they don't touch the neural network that's used to compute these probability distributions. You're just kind of changing these distributions a little bit, reweighting them as you sample the next token. Okay, and so a very simple way that you can change this distribution is to partition all words into a green list and a red list. And now simply increase the probabilities of the words on the green list and decrease the probabilities of the words on the red list. And now detecting the watermark is also very simple. If you're given some text, what you do is you just count the fraction of words in that text that are green, and the higher this fraction is, the more confident you can be that the text was watermarked. But unfortunately, kind of changing these probabilities can have some bad consequences. For example, you might end up increasing the probability of green words that don't make so much sense in this context, and so you can change the quality of the responses. Here, we accidentally end up saying that a good low-energy dog is a husky because we increase the probability of husky, while it's actually not a very low-energy dog. Okay. And so a natural question we might ask as theorists is whether this detectability quality trade-off is actually fundamental. And so we could try to formalize this by saying that here, if we look at the original model's distribution of essays, if our model was any good, then this distribution should be close to the human-generated essays, where our detector needs to output false. Right, because we want a low false positive rate, we need to output false on these human-generated essays, and this distribution is close to the original model's distribution, and so here the detector has to output false as well. But for our watermarked essays, we wanted the detector to output true. And so this actually implies that these two distributions are far in statistical distance. And so this is why the notion of quality that I put up at first maybe is not such a good one. You don't actually want to require that these two distributions are close in statistical distance because this rules out the possibility of a detectable watermark. Okay. So what we've shown here is that if you have detectability, then you can't possibly have quality if quality is closeness in statistical distance between these distributions. Okay. But let's take a step back and think about what quality notion we actually want. Statistical distance was a bit arbitrary. But maybe one problem we run into is that formally defining quality of an LLM seems to be a hard task in itself. It's hard to say like what a high quality essay is, and it only gets harder as you're using an LLM on lots of different tasks. But in practice, the way that we measure quality is often with experiments. So we'll have some efficient experiment that we run to measure quality, maybe by running benchmarks, using human feedback, or actually deploying the model and seeing how it does on tasks that we use it for. And so it's good enough to say that the watermark doesn't harm performance on any experiment, on any possible downstream task we could use the model for. Kind of for all practical purposes, this is the best quality notion that we could really ask for. And so what we can do now is define quality in terms of computational indistinguishability. Right, it's enough as long as no efficient algorithm can distinguish between the original model's distribution and the watermarked model's distribution. We don't need them to be close in statistical distance. It's enough for them to be indistinguishable to any efficient algorithm. And so we can define this using a game-based definition. This is called undetectability, where you have some distinguisher that can make adaptive queries to either the original model or the watermarked model. It doesn't know which. And at the end of this experiment, it needs to say whether it thinks it was talking to the watermarked model or the original model. And we say a watermark is undetectable if any efficient distinguisher has negligible advantage in this game. Okay. And so now we can replace our old quality definition with this computational indistinguishability based definition. But note that now we'll actually need a secret key to detect the watermark because without the secret key, these two distributions are indistinguishable. Okay. So just like revisiting our picture, it's possible to have these two distributions very statistically far, but computationally close. And this is now the quality definition that we'll focus on.
Is it actually clear that they need to be statistically far once you introduce the secret key? Because maybe you can only distinguish given the secret key.
They're still statistically far because the detector needs to output false on all of on the human distribution, which is close to the original model's distribution, and it needs to output true on the watermark distribution. And so this like exactly implies that they're far in statistical distance. But you could hope for some kind of like single sample statistical closeness. So maybe one sample from the watermark distribution is identically distributed to one sample from the original model's distribution. And this is easy to achieve, and I'll touch on it a bit later. Okay. Okay, so far it seems possible to maybe get undetectable watermarks, like undetectable meaning this quality notion I just showed you, that are also highly detectable using a secret key, but I haven't told you anything about how we can actually construct them. So I'll do that next. And what I'm going to tell you is going to seem maybe a bit like a thought experiment at first, so you'll need to kind of believe what I'm saying. But what I want you to think of is, say, consider generating a response using the model. And now every time the model samples a token, first we're going to flip a coin. And if the coin comes up heads, we'll increase the probability of the green words. Otherwise, we'll increase the probability of the red words. So I'm not going to tell you yet what we're doing with these coins, but just imagine doing this. And notice that this actually exactly preserves the model's output distribution if we do these increases in a balanced way. Right? Half the time we're increasing green, half the time we're increasing red. So on the whole, we're not introducing any bias to the distribution at all. And then also most of the time when the coin was heads, since we increase the probability of green, the token that we actually end up sampling will be green. But note that, sometimes, even though we increase the probability of green, we'll still happen to draw a red token. So what we'll end up doing if we sample a sequence of tokens is it'll look something like this. Sometimes, most of the time when we draw heads, we'll get green, but sometimes when we draw heads, we get red, say in the word of. And so what I've shown you is a way to think of the model as taking, in addition to its input, some random tape, it's the sequence of coin flips, such that the content that it samples will be correlated with the random tape. So if you looked at the sequence of coin flips, they would tell you what the colors of most of the sample tokens are. Not perfectly, but most of the coin flips will correspond to the color of that token. Yeah, so most of the time when the coin was heads, the token will actually be green. And so the coin flips are really correlated with the sequence of tokens, but don't match exactly. There are some errors that are introduced. And taking a step back and saying it a little bit more formally, you can show that for language models, there is some, what I'll call an unbiased seed correlated sampler that you can think of as taking the model and the prompt and some additional randomness and resulting in a distribution that is identically distributed to the original model on that prompt, but such that if you sample a text using this unbiased seed correlated sampler, and you convert the text to binary, so you use the colors of the tokens to map back to heads or tails or 0 or 1, then the string that you get back is close to the string that was used by the sampler in Hamming distance. So if you use this unbiased seed correlated sampler to sample responses, there is some way to recover an approximation of the seed used to sample that response. But this will be a bit lossy. What you recover is close to the original seed in Hamming distance, but it's not exact. Yeah, question?
So this seems like being as expensive as like just remember everything that LLM has generated and then see if whatever you have is one of the things that LLM generated.
So far, all you need to do to recover the seed is take the response, look at the partition into green and red, and use the colors to recover the seed. If you wanted to remember all of the seeds used so far, then yes, this would be very expensive, and so we'll want to avoid doing that. But that is a way to use this to get a watermark immediately. Just remember all the seeds, and then if you get a text, just check closeness of this seed you recover to any of the ones you actually used. And so you can actually prove that for LLMs, if the response has high enough entropy, then the seed that you recover will equal the seed that you actually used for many more than half of the bits. So you can kind of bound the error rate in terms of the amount of entropy in the response. Yeah, and so I redrew this picture with this approximate randomness recovery. You can think of using the red-green assignments and converting to binary as some algorithm that takes the content and approximately recovers the seed that was used to generate it. And it actually turns out that this approximate randomness recovery exists for generative models beyond LLMs, but for now I'll just focus on LLMs. Okay. I'll skip through this a little bit. And so what we get gives us a very common watermark blueprint that you can actually think of as representing a lot of schemes in the literature. And the idea is that instead of using a uniformly random seed to generate each response, you can choose these seeds from a special structured family. And now use the unbiased seed correlated sampler with the seed to generate the response. And to detect the watermark, once you use your approximate randomness recovery, you just check whether the string that you got is close to something in the special structured family. And so now this could be much more efficient than just storing all of the seeds that you've ever used. And so we'll see a couple instantiations of this scheme. Okay, and so maybe the first instantiation you might think of is using an error correcting code to choose these seeds that you use, right? So maybe you have some error correcting code and you use a random code word as your seed. And so what you can do to detect the watermark is convert to binary and check if what you get is close to a code word from this error correcting code. And so this watermark is actually fairly easy to detect. And it also has the nice property that if someone goes and changes a bunch of words in the response, this is simply introducing more errors to the code word. And so your watermark can actually withstand some changes to the word of the text. But one problem here is, remember our goal was undetectability, right? We wanted the watermarked model to be computationally indistinguishable from the original model. And now we've gone and replaced the randomness used by the sampler with code words. And so we don't really know how this is affecting its distribution. And in particular, you could think of using a bad error correcting code, say one where the only code word is all ones. And now replacing the seed with this all one string actually amounts to just partitioning all of the words into red and green and increasing the probability of the green words again, right? This is...
So sorry to interrupt you.
Okay.
There you go.
This is the same as if the coin came up heads every single time, and so we're just increasing the probability of green on every word, and we're back to exactly where we started. And so the kind of main idea of this talk is, instead of using a regular error correcting code, to use a special error correcting code that is actually pseudorandom. And so a pseudorandom code, which I'll define in a bit more detail in a couple slides, you can think of as a combination between an error correcting code and pseudorandom encryption. So it's a keyed error correcting code where code words are pseudorandom. Any polynomial number of code words are computationally indistinguishable from uniformly random strings. And so if you replace your seeds with these pseudorandom code words, then since they look uniform to any efficient algorithm, the distribution of content that you end up with is computationally indistinguishable from the original model's content. And so applying pseudorandom codes with this unbiased seed correlated sampler, you immediately get robust and undetectable watermarks for LLMs. Okay. And as a quick aside, I'm going to use this unbiased seed correlated sampler framework to describe a couple of other schemes in the literature. And maybe this will show you why I think pseudorandom codes are really the right object to use. And so there were a few schemes that you can think of as using a PRF applied to previous tokens in the response to kind of generate the seed on the fly. So you would generate the next bit of the seed by applying a PRF to, say, the previous 3 tokens that you output. And now to detect, you need to rederive the seed by using the PRF. And so I won't say too much about this, but this ends up having kind of a bad trade-off between the number of tokens you input to the PRF, which gets you better quality, but worse robustness. Now, if any of those tokens are changed, you can't recover the PRF output, and so you can't tell what the seed was. Okay. There's a better version of the simple red-green scheme we saw before that you can basically think of as using a fixed seed that's all ones that results in globally increasing the probability of green words. And now you can think of detection as computing distance to this all ones seed. You could also consider using a fixed random seed, which is kind of what Daniel maybe was asking about. And now you get the property that a single response from the watermarked model is identically distributed to a single response from the unwatermarked model. But if you see multiple responses, then you might start to see correlations. Another thing you could imagine doing is, as a seed, you could use something like a pseudorandom signature, and this could get you an unforgeability property of the watermark. I won't say too much about this, but you can see that by sort of changing the seed, you can get all kinds of different properties of your watermark. Finally, there's a pseudorandom code-based approach where you replace the random seed with a pseudorandom code word, and now to detect, you effectively check distance to a code word by running this decoding algorithm that comes with the pseudorandom code. And so now for the remainder of the talk, I'll focus on pseudorandom codes. Does anyone have the time?
I do, I guess. You have about like 30 minutes?
Okay, great.
Like 20, 25, 30 minutes?
Okay. Okay, so what is a pseudorandom code? It is, I think, a fairly simple cryptographic primitive. The first property that pseudorandom codes have is ciphertext are pseudorandom. So what this means is oracle access to the encoder on messages of your choice is computationally indistinguishable from oracle access to just a uniform distribution. So in particular, if you encode even the same message over and over again, all of the code words or ciphertext that you get back will be indistinguishable from random. The other property is that ciphertexts are robust to error. So if you have the encryption of some message, the encryption of some message with some low weight error, sorry, this should be, the weight is much less than n over 2, say some constant less than 1/2 times n, then this should still decrypt to the message. Okay. Any questions about these properties? Again, the weight should be a constant less than 1/2 times n. Okay. And so you can visualize a pseudorandom code, say, by plotting encryptions of 1 on the binary hypercube. These should look like random points. And then robustness says that if you draw fairly large Hamming balls around them, nearly everything in these Hamming balls should still decrypt to 1. And so what this gets when applied to watermarks is that it's hard to remove the watermark. Okay. And so when thinking about constructing a pseudorandom code, maybe the first thing you would think of is trying to combine a pseudorandom encryption scheme with an error correcting code. So if you're less familiar with cryptography, we actually know how to get encryption schemes where ciphertexts are pseudorandom using only one-way functions. So it's fairly easy to get pseudorandom encryption. And of course, we have all kinds of good error correcting codes. So a natural way to construct pseudorandom codes might be to combine these objects in a generic way. But if you try some things out, you can see that if you first encode the message and then encrypt it, what you get is pseudorandom, just by pseudorandomness of encryption, but it's not robust at all in general. And in fact, if you take maybe the most basic pseudorandom encryption scheme, what you get involves evaluating a PRF on some first portion of the ciphertext R, and if any bit in that portion is changed, then you can no longer recompute the PRF, and so you can't decrypt at all. On the other hand, if you first encrypt the message and then encode it, now what you get is in general not pseudorandom. One concrete way to see this is by thinking about the repetition code. Now, it kind of doesn't matter what encryption scheme you used. If you look at a repetition encoded code word, like you can see that it's obviously not pseudorandom. And it turns out that any example you try will fail, and this is actually true in general. There were 2 works at TCC this past year that showed that no generic black box combination of encode and encrypt succeeds at constructing a pseudorandom code. So they're kind of a new cryptographic primitive separated from pseudorandom encryption. But I'll give an overview of a fairly simple construction of a pseudorandom code. And the starting point for this is LPN. And so LPN, or learning parodies with noise, is a fairly standard cryptographic assumption, which basically says that noisy samples from a random linear code are pseudorandom. So if you have a random generator matrix G, and you have a bunch of samples GS plus E, where S is random and E is random and low weight, then this is computationally indistinguishable from G and a uniformly random vector. And this is true for any polynomial number of samples. And so one way we might try to construct a pseudorandom code using this assumption is to say, to encode 0, we can output a random string, and to encode 1, we can output a noisy sample from a random linear code. And so LPN immediately tells us that this is actually pseudorandom. We can't distinguish between these 0 and 1 encryptions and uniformly random vectors. But what LPN also tells us is there's no way to distinguish between our encryptions of 0 and our encryptions of 1. Exactly because we can't distinguish between these noisy random code words and uniform. And so the idea behind this construction is just to sample our generator matrix along with a trapdoor that will let us distinguish. So this is actually going to be the way that our encoding algorithm works, but our decoding algorithm will take some extra information that was sampled alongside the generator matrix that lets us distinguish efficiently. And so this extra information is going to take the form of a very sparse parity check matrix H. So each row in H is going to have only log n ones. It's going to look something like this. And now we sample our generator matrix G subject to H times G equals 0. And what this gives us is that if we have some noisy code word GS plus E and we multiply it by the parity check matrix, then what we get is just H times E. And since the rows of H are sparse, if E has low weight, then H times E will actually have lower weight than you would expect compared to H times a random vector. So multiplying by H will let us distinguish between noisy code words and random vectors. And maybe another thing I'll note is if we want to invoke LPN, which only tells us about random linear codes, then we'll actually need to show that G sampled in this way is random. And so we showed that if G is narrow enough, then it's in fact statistically close to random. Okay. So to recap our scheme very quickly, this actually gives us a public key encryption scheme, where the public key is the generator matrix. The secret key is the sparse parity check matrix H. To encode 1, we will output a noisy code word. To encode 0, we'll output a uniformly random vector. And now to decode, we multiply by H and look at the weight. And since H is sparse, it'll turn out that noisy code words will have lower weight than we would expect compared to random vectors when we multiply by H. Okay. And so this construction tells us that you can actually construct pseudorandom codes under standard cryptographic assumptions, in particular, sub-exponential hardness of learning parity with noise. And you might be wondering where the sub-exponential hardness comes from. That is just because in order to show that G was random, we needed to take it to be very narrow. And so this results in basically the security parameter being small, which requires us to use a stronger version of LPN. Okay. And so plugging this construction of pseudorandom codes back into the watermarking blueprint, where we replace the seed with a pseudorandom code, this gets us robust and undetectable watermarks. In particular, the watermark persists even if you change a constant fraction of the words in the text. Okay. Yeah, and so this shows us that it's actually possible to get a watermark that is both undetectable and robust. So robustness is even stronger than detectability. Not only can we detect the watermark and content output exactly by the model, we can still detect it even if this content is significantly changed. And okay, now I want to tell you a bit about subsequent work on pseudorandom codes, and there is quite a bit of it at this point, and so the slide is a little bit like intentionally information overload. I think this is an exciting area to work on, and there are a lot of open questions that have been looked at from works ranging from ML conferences to crypto conferences to STOC, and so yeah, here's a little taste of some of this work. In particular, I mentioned before that you can think of generative algorithms beyond LLMs as having this randomness recovery that lets you approximately recover the seed. It turns out that image models have this as well. And so you can use this seed recovery watermarking framework for image models, and using pseudorandom codes actually get an undetectable image watermark. So Sam with his co-authors from Berkeley implemented such a watermark. They generated real images that are watermarked. So it's not just like pseudorandom codes and watermarks are not just a theoretical object. They can actually and have actually been implemented. And Cloudflare prototyped a pseudorandom code-based watermark for stable diffusion as well. I'll also mention that Noah is talking about a newer work on pseudorandom codes in a couple of hours. And so that has kind of the newest construction of pseudorandom codes with some fairly strong properties. So if you're interested in what kind of the best properties of pseudorandom codes we have right now are, you should go to Noah's talk. And then I'll also mention that since pseudorandom codes are fairly hard to construct, right, we couldn't do it generically using existing cryptography, they have led to a lot of new cryptographic assumptions being introduced. A few very recently, these preprints that I have up were put on ePrint, I think, within the last month. And so I think there's a lot of work to be done analyzing these assumptions and maybe trying to break some of them. So yeah, these are basically a bunch of new code-based assumptions where I think they've been introduced mostly by cryptographers, and maybe the coding theory community can have something to say about whether they can be broken. Yeah.
So can you tell a bit about the loose embeddings paper? Maybe a sentence about like what kind of like does the pseudorandom codes give you new like improvements for error correction, traditional error correction too?
Yeah, so you should probably talk to Daniel about this for the full details, but what I think the paper does is it uses pseudorandom codes to construct better error correcting codes against computationally bounded errors. But you should ask Daniel probably. Okay. And so far, I kind of swept under the rug what kind of robustness pseudorandom codes have. If you were paying really good attention, you might have noticed that the construction that I just showed is actually only robust to random errors. And if someone is trying to remove your watermark, they're probably not going to introduce random errors. But we do have the nice property that for watermarks, changing each word of the text corresponds to adding an error to a code word. And so if you can construct pseudorandom codes with better robustness, this translates immediately to better robustness of the watermark that you get. Right, like all we did is we used colors to convert the text to a binary string and checked if it was close to a code word. And so if you change one word, then that just changes one bit. Okay. And revisiting the picture I showed you of a pseudorandom code, this also is sweeping some stuff under the rug. I said that nearly all strings in these Hamming balls should still decrypt to 1. If you kind of, okay, yeah, maybe as an aside, why do we have the balls to begin with? You might want to say that it's hard for any efficient adversary to remove the watermark, but this is unachievable because if an efficient adversary can write English, then they can just write the essay themselves, ignore the model completely, and now it won't be watermarked. So kind of the best robustness you can hope for is robustness against some constrained class of adversaries. And the most common constraint in the literature is just that the adversary cannot change too many words. Question?
Would you still think about some reduction? I would say that if the adversary is breaking it, then you could have written it himself, so we don't want to protect against such adversaries.
Yeah, you could, but we actually have a result in my paper with Sam and Orr, undetectable watermarks, where we show that any undetectable watermark can be removed just by querying the model enough. So for any undetectable watermarking scheme, for any prompt, an adversary can query the model and get a response to that prompt that is distributed very close to how it would be from the original model, and it is not watermarked. So you could consider that kind of reduction. That also turns out to be unachievable for undetectable watermarks, and that has been formally shown. Yeah, it's in undetectable watermarks with Sam and Orr. Yeah. Okay. But actually, if you zoom in on one of these Hamming balls, it turns out that many notions of robustness of pseudorandom codes, and in fact, the scheme that we just saw, all they tell us is that the number of strings, or the strings that decrypt to 0 within this Hamming ball, there aren't too many of them. So if you represent them as red dots, then there should be very few red dots within this Hamming ball. But it might actually be easy for an adversary to find the red dots, right? Like it could be easy for an adversary to find error or find changes to the words that causes the watermark to disappear. So a better kind of robustness would not just be that there are few low-weight error vectors that cause incorrect decoding. We actually want these error vectors to be hard to find by efficient adversaries. And in particular, if an adversary can query encoding and decoding oracles, or in practice, if they can see watermarked responses and query a watermarked detector, which reveals information about the underlying code words, then this might tell them something about the location of these red dots. This might help them find some low-weight error that they can introduce to cause incorrect decoding. And so this problem led to the introduction of a new kind of pseudorandom code with stronger robustness. It's called an ideal pseudorandom code. which requires that the encoding and decoding oracles kind of look like oracles in a world where there are no red dots. So the encoding and decoding oracles should be computationally indistinguishable from some ideal encoding and decoding oracles, where the ideal oracles are stateful, and what they do is the encoder responds to each query with a uniformly random string. It records all of these query response pairs. So here, the ideal encoder is outputting actually random code words. And the ideal decoder, given some C prime, looks in the list of all of the code words it's output before, sees if C prime is close to any of them, and outputs the corresponding message if so. And so the ideal encoder and decoder basically implement a very large, truly random code, which of course is not efficient, but the pseudorandom code itself must be efficient and indistinguishable from this ideal functionality. Okay, and so yeah, we showed that these ideal pseudorandom codes exist under the same assumptions as the construction from earlier. I'll skip over the full results, but basically, in studying these ideal pseudorandom codes, we really just solved a purely theory question, but this had implications for watermarks. So by plugging these pseudorandom codes into the framework, now we get a watermark where it's hard for an adversary to remove it, even if they can query the watermarked model a polynomial number of times and also query a detection oracle. And so I didn't really show the results of this paper, which was from STOC last year with Omar Al-Rabia, Prabhanshan Ananth, Yevgeny Dodis, and Sam Gunn. But what I want to emphasize here is that now that we've reduced the problem of building watermarks to just building pseudorandom codes, you can build improved pseudorandom codes, not need to touch AI at all, and get an improved watermark for AI-generated content. Okay, and a small teaser for Noah's talk. Again, we construct an improved PRC, and so this gets an improved watermark. And I'll gloss over exactly what we do. Okay, so now I want to end with some open questions about pseudorandom codes that hopefully some of you might be interested in working on. And I also have a lot more questions that I won't have time to cover, so please feel free to talk to me after if you're interested in any of these, or maybe if you think of anything else yourselves. And so one question is whether you can take a pseudorandom code that is robust to substitutions, like changing the bits, and somehow boost it to a pseudorandom code with the same kind of robustness as substitutions, but tolerating a higher rate of errors. And you could hope to do this by combining a pseudorandom code with just a standard error correcting code in some clever way. So the hope would be that you can take a standard error correcting code with much higher robustness than the pseudorandom code and somehow inherit that greater robustness. Another question is whether we can upgrade the kind of robustness. So say you start with a pseudorandom code that tolerates changing the bits. Can we upgrade it to one that tolerates also inserting and deleting bits, where the error tolerance, or like the rate of error that you tolerate, isn't lost too much? So in particular, we want to go from tolerating a constant rate of substitutions to tolerating a constant rate of edits. And there are a couple transformations that do something along the way to this. There's one by Golowich and Moitra that goes from substitution robustness to edit robustness, but requires a much larger alphabet for the edit robust PRC. Here, I really want to go from binary to binary. There's a newer paper that does this as well. I can talk about this more offline, but again, it has a much lower error tolerance for the edit robust PRC. In particular, it goes from constant to just 1/poly, which is a fairly large loss. Yeah, for substitution robustness, we don't actually know anything. Okay, another question that I would really like to see looked at is whether we can show attacks against any of these new crypto assumptions that were introduced to build pseudorandom codes. This might be low-hanging fruit because a couple of these papers were really just put out, And so some of these assumptions have not really been looked at all. Another thing I would really like to see is more cryptographic applications of pseudorandom codes. So the black box impossibility that I mentioned really shows that pseudorandom codes are a different object from other crypto primitives. Maybe this means they're more powerful than other crypto primitives. So far, they haven't been shown to be useful in cryptography for much more than watermarks. Maybe Daniel's paper on error correction against computationally bounded channels is maybe the only example I know of a cryptographic application beyond watermarks. And so it would be very interesting to see more applications. And I have like specific questions under this that I'm happy to talk about more. Again, applications of pseudorandom codes but to theory would be very interesting. You can think of an ideal pseudorandom code as implementing a truly random code with a super polynomial sized code book where you can still do efficient decoding. This seems like a powerful object. Nobody's really done anything with it yet. Yes. Okay, and so these are actually all of the open questions that I have in the slides, but again, I have a lot more that I can talk about offline. I'll also mention that I'm working on a survey on pseudorandom codes that has a lot of what was in these slides and a lot more and more open questions. And so if you want a copy of that, please email me. I'll also hopefully post it soon. And yeah, I'm very happy to talk to anyone about watermarks or pseudorandom codes. And in particular, I'd love to help people get started working on open questions. So thank you.
We have a lot of time for questions, so.
Can you say a little bit more about what the robustness guarantees, like that we have in theory, what they translate to kind of in practice with LLMs, and whether from a practice point of view we're sort of like satisfied with those kinds of robustness, or the watermarks are kind of still too easy to remove with something that still should be considered as AI content. Like for example, if I took the essay and then I ran it into Google Translate to translate into French and then translate back to English, maybe that would, presumably that might remove the watermark, but maybe that shouldn't be considered AI generated content. I'm just curious where the current thinking is around those sort of issues.
Yeah, okay, so I have a lot to say about this question. One is that an open question, that's actually one of my favorites that I didn't put on here, is constructing watermarks with semantic robustness. So you could imagine that maybe the watermark is embedded in the semantic space of the response. And so any text that is sufficiently semantically close to what the model output will still be watermarked. So even if you change every single word, as long as the meaning remains, then the watermark should still be there. And this seems possible in principle. It's turned out to be hard. But I have some starting points if you want to construct something like this. Still think it's hard. So yeah, that's kind of a more practical kind of robustness. And that would address this translation issue. I think, okay, you also touched on whether something should be considered AI generated. People have considered something maybe a bit stronger than, but different from robustness, which is like recoverability. So for some watermarks, not only can you detect whether the content is watermarked, you could recover the prompt and the response that was output by the model. And so now if you have this, you can let a human judge whether they feel this is significantly AI generated. And so that would be really good for, say, detecting plagiarism or something like that. And now whether we're satisfied with this kind of substitution or like edit robustness in practice, it's unclear. I think the watermarks that are deployed now are probably edit robust, but not semantically robust or anywhere close to that. And that's because they kind of follow the PRF-based approach that I touched on briefly. So you like take the last few tokens that you generated, input those to a PRF to get some randomness to bias the next token. And so this kind of watermark will not have any kind of semantic robustness because you're inputting the exact tokens to the PRF. So that is what Google's scheme does. Okay, but that's all text. Now for image watermarks, I'm not completely sure what schemes they use in practice, but kind of more semantic image watermarks are practical. So Sam's paper really embeds the watermark in the latent space of the image. And the latent space represents the higher order features of the image. And so now you get the property that as long as those features are preserved, you can still detect the watermark. And I believe that the watermarks deployed right now also are embedded in latent space. I'm not 100% sure. So for images, I do think you wouldn't be satisfied with kind of pixel by pixel change robustness because the pixels change all the time without anyone trying. Just because of like how the image is represented, maybe people edit the brightness or something like that. Often a lot of pixels will change without an adversary trying to remove the watermark. So for images, you want semantic robustness and it's also easier to achieve. So yeah, that was a lot.
Great. Yeah.
Did that answer your question?
Yeah, super helpful. Thanks.
I think maybe unless the question is super quick, maybe we should break. Is the question super quick?
Okay, I just want to ask if there's any notion of like public verifiability that makes sense.
Oh, yes. But the question, okay, so you can always get public verifiability by just publishing the detection key. Now the question is what you might lose by publishing the key. Like maybe it'll make it easy for an adversary to forge the watermark. That definitely is true. For most schemes. Maybe it'll make it easier for the adversary to remove the watermark. And so people have considered watermarks with public unforgeability or watermarks with robustness, even if you publish the detection key. Both of these make sense and have been considered.
Let's thank the speaker again.